Welcome to an exploration of quantum tunneling, one of the most mind-bending phenomena that powers modern nanotechnology. Imagine an electron that can pass through solid barriers as if they were transparent. This isn't science fiction, it's quantum tunneling, and it's happening trillions of times per second in your smartphone right now. Let's start by understanding why quantum tunneling seems impossible from a classical physics perspective. In classical physics, imagine rolling a ball toward a hill. If the ball doesn't have enough energy to reach the top, it simply rolls back down. The ball needs sufficient kinetic energy to overcome the potential energy barrier of the hill. Without enough energy, crossing is impossible. Mathematically, if kinetic energy is less than the barrier energy, classical physics says there's no crossing. Period. But here's where quantum mechanics completely breaks this classical rule in a fascinating way. In quantum mechanics, particles behave fundamentally differently than classical objects. The key insight is that electrons aren't tiny balls. They're described by probability waves that spread out in space. This is a quantum wave function. The height at any point tells us the probability of finding the electron there. The wave function psi describes the electron's quantum state. It contains all information about the particle's position and momentum. The probability of finding an electron at position x equals the square of the wave function's magnitude at that point. Now let's understand what a quantum barrier actually represents in the atomic world. A quantum barrier is simply a region where the electron's potential energy would be higher than its total energy. Here's a potential energy diagram. The red barrier represents a region of high potential energy. The yellow line shows the electron's total energy, which is less than the barrier height. In real electronics, these barriers are thin layers of insulating materials, like silicon dioxide, only a few nanometers thick. For silicon dioxide, the barrier height is approximately 3.2 electron volts. That's a huge energy compared to thermal energy at room temperature. Now we arrive at the heart of quantum tunneling, the probability that an electron can pass through a barrier. The tunneling probability T is approximately exponential in -2 kappa L, where L is the barrier width. Here, kappa equals the square root of 2 meters times V0 minus E divided by h bar. This is the decay constant inside the barrier. Let's carefully examine what each symbol in this crucial equation represents. M is the electron mass, equal to 9.11 times 10 to the negative 31 kilograms. V0 is the barrier height, the potential energy inside the barrier region. E is the electron's kinetic energy, which is less than V0 for tunneling to be interesting. H bar is the reduced Planck constant, approximately 1.055 times 10 to the negative 34 joule seconds. And L is the physical thickness of the barrier in meters. Let's calculate an actual tunneling probability to see how dramatic this effect can be. Consider a barrier of silicon dioxide just 1 nanometer thick, that's about 3 or 4 atoms across. L equals 1 nanometer, which is 10 to the negative 9 meters. Let's say the energy difference between the barrier and electron is about 2 electron volts, or 3.2 times 10 to the negative 19 joules. Plugging into our formula for kappa, we get the square root of 2 times 9.1, 1 times 10 to the negative 31, times 3.2 times 10 to the negative 19, all divided by 1.05, 5 times 10 to the negative 34. This gives us kappa approximately equals 7.26 times 10 to the 9th per meter. So 2 kappa L equals about 14.5, a dimensionless number. Therefore, the tunneling probability is e to the negative 14.5, which is approximately 5 times 10 to the negative 7, or about 0.00005. This means roughly 1 in 2 million electrons successfully tunnel through this 1 nanometer barrier. That might sound small, but with trillions of electrons, it's actually significant. Here's the crucial insight. Tunneling probability depends exponentially on barrier thickness. This graph shows how tunneling probability drops exponentially as the barrier gets thicker. Even a fraction of a nanometer makes a huge difference. If we double the barrier thickness from 1 to 2 nanometers, the tunneling probability doesn't just halve, it drops by a factor of about 1 trillion. This exponential sensitivity is precisely why nanotechnology, the ability to control matter at the atomic scale, is absolutely essential for practical tunneling devices. But what actually happens when an electron tunnels? Let's visualize this quantum process. The electron's wave function extends into and through the barrier. Before the barrier, the wave oscillates normally. Inside, it decays exponentially, but doesn't vanish. After the barrier, it oscillates again with reduced amplitude. The electron doesn't physically dig through the barrier or go around it. It exists as a probability wave that extends through the classically forbidden region. Quantum mechanically, the electron exists in a superposition state, simultaneously reflected and transmitted, until a measurement collapses this superposition. Now let's see how tunneling is exploited in real electronic devices, starting with the tunnel diode. A tunnel diode consists of heavily doped p-n junction with a very thin depletion region, only about 10 nanometers wide. Electrons can tunnel directly from the inside to the p-side. Because tunneling happens at the speed of light divided by the effective distance, tunnel diodes can switch incredibly fast, in picoseconds, making them useful for high-frequency applications. The tunneling time is approximately the barrier width divided by the electron velocity, giving times on the order of 10 to the negative 13 seconds, or 1/10 of a picosecond. Quantum tunneling presents both opportunities and challenges in modern nanotransistors. Modern transistors have gate oxide layers less than 1 nanometer thick. At this scale, quantum tunneling becomes unavoidable and electrons leak through the gate. As transistors shrink below 20 nanometers, gate leakage current due to tunneling increases exponentially, wasting power even when the transistor is supposed to be off. Leakage current is proportional to exponential negative alpha times oxide thickness. This is the same exponential relationship we saw earlier. At the 5 nanometer technology node used in modern processors, tunneling leakage has become one of the major power consumption mechanisms, limiting further miniaturization. Flash memory brilliantly exploits quantum tunneling to store data permanently without power. Flash memory has a floating gate surrounded by insulating oxide. Electrons tunnel onto this gate when programming and tunnel off when erasing, but stay trapped for years when no voltage is applied. During programming, a high voltage causes electrons to tunnel through the oxide onto the floating gate, where they become trapped. The stored charge persists for more than 10 years because the tunneling probability at zero voltage is vanishingly small, essentially zero. The theoretical retention time is proportional to exponential positive 2 kappa L, which works out to billions of years for thick enough oxide. When erasing, applying the opposite voltage makes electrons tunnel back off the floating gate, resetting the memory cell. One of the most beautiful applications of quantum tunneling is the scanning tunneling microscope, or STM. The STM uses an atomically sharp metal tip positioned within a nanometer of a surface. Electrons tunnel between the tip and surface, creating a measurable current. The tunneling current is exponentially sensitive to the tip surface distance. Moving the tip just 1 angstrom closer increases current by a factor of 10. Current is proportional to exponential negative 2 kappa d, where d is the gap distance. This extreme sensitivity allows atomic resolution. Invented in 1981, the STM was the first instrument to image individual atoms, revolutionizing nanoscience and earning its inventors the Nobel Prize. Quantum tunneling also plays a crucial role in emerging quantum computing technologies. Josephson junctions, where superconducting layers are separated by thin insulators, rely on Cooper pair tunneling to create quantum bits or qubits. In superconductors, electron pairs called Cooper pairs can tunnel through barriers while maintaining quantum phase coherence, essential for quantum computation. The current through a Josephson junction equals IC times sine of delta phi, where delta phi is the quantum phase difference. This is the Josephson effect. This tunneling phenomenon enables superconducting qubits used in quantum computers from companies like IBM and Google, operating at temperatures near absolute zero. As we push technology smaller, quantum tunneling presents both opportunities and fundamental limits. Below 1 nanometer thickness, tunneling becomes so strong that traditional transistors cannot be turned off effectively. This represents a fundamental physical limit. We're approaching the quantum limit, where Moore's law, the exponential growth of transistor density, must end. The laws of quantum mechanics themselves become the constraint. Researchers are exploring solutions including new materials like graphene, three-dimensional chip stacking, and entirely new computing paradigms based on quantum or neuromorphic principles. Let's consolidate some practical numbers that engineers actually use when designing tunneling devices. For silicon dioxide barriers, engineers work with a barrier height of 3.2 electron volts and typical thicknesses of 1 to 2 nanometers. Typical tunneling current densities range from 1 to 100 amperes per square centimeter, depending on the application. The Fowler-Nordheim equation gives current density J approximately as 10 to the 6th times voltage squared over thickness times exponential negative beta d times square root of phi, where phi is the barrier height. A useful rule of thumb: tunneling current increases by a factor of 10 for every 0.1 nanometer reduction in barrier thickness. Let's think about tunneling from an energy perspective to deepen our understanding. From an energy diagram, we see the electron has less energy than the barrier height. Classically, this electron cannot exist inside the barrier region at all. However, Heisenberg's uncertainty principle allows brief violations of energy conservation. The electron can borrow energy delta E for a time delta t, provided their product is less than h bar over 2. Delta E times delta t must be greater than or equal to h bar over 2. This fundamental quantum limit permits tunneling. The electron essentially borrows the energy needed to cross the barrier and pays it back immediately upon exiting. This doesn't violate energy conservation on average. Let's step back and appreciate why quantum tunneling is absolutely central to modern technology. Your smartphone performs billions of tunneling events every single second in its processor, memory, and storage devices. Without quantum tunneling, we would have no flash memory for data storage and no modern CPUs with billions of transistors. Our technological civilization depends on this quantum effect. The exponential growth in computing power over decades has been possible only because we learned to control and exploit quantum tunneling at the nanoscale. The understanding and control of quantum tunneling underlies the trillion-dollar global semiconductor industry that powers our digital economy. Let me give you a striking analogy to help internalize how strange tunneling really is. Imagine you're throwing tennis balls at a brick wall thousands of times per second. Classical physics says they'll all bounce back, but quantum mechanics predicts that occasionally, randomly, a ball will appear on the other side without breaking the wall. Now scale this down to the quantum realm of electrons and nanometer barriers. Electrons perform this magic trick constantly, trillions of times per second in your devices. It's not magic, it's quantum physics. The wave-like nature of matter makes this behavior completely natural at atomic scales. Let's summarize the key concepts we've explored about quantum tunneling. First, electrons behave as probability waves, described by the wave function, not as classical particles. Second, these wave functions can penetrate into and through classically forbidden barrier regions, with exponential decay. Third, tunneling probability follows the exponential formula, T approximately equals exponential negative 2 kappa L, making it extremely sensitive to barrier thickness. Fourth, tunneling enables crucial technologies including transistors, flash memory, scanning tunneling microscopes, and quantum computing. And fifth, tunneling represents a fundamental quantum limit to how small we can make conventional electronic devices. As we conclude, let's reflect on the profound implications of quantum tunneling. Quantum mechanics is not some abstract theory disconnected from reality. It's the engineering reality that billions of people interact with every day through their electronic devices. Looking forward, emerging quantum technologies will exploit tunneling even more deeply in quantum computers, quantum sensors, and quantum communication systems. We stand at the threshold of a quantum technological revolution, built on our understanding of phenomena like tunneling that seemed impossibly strange just a century ago. In just 100 years, we've gone from discovering the quantum weirdness of tunneling to building a global civilization that depends on it. That's the power of understanding nature's deepest laws.